One of our main ways to classify and organize thermodynamic variables is to decide whether they are called intensive or extensive. Of course, we need to know what those words mean first. So let's figure that out, and we'll go through an example where we learn what quantities are intensive, extensive, and basically how they scale with the size of the system. So let's consider a large thermodynamic system. It could be a gas, it could be a liquid, it could be a solid, but it's big, and we're only going to look at a small region of it. So we've got this big area of matter. It's all doing its equilibrium, thermodynamic stuff. And we're going to look at some small region in the middle of a volume V. Okay? Now, considering this as our sort of sample of matter, what quantities could we measure for this? Well, we obviously chose the volume, but we could also measure, say, its number of molecules, right? Just basically how many dots are in this box, right? How many molecules are in that volume? So number n. We could be more chemistry minded and say it's moles instead of number. We could also measure the total internal energy. Here I'll just say internal U. We could, add up the motions of each of these particles and have its internal energy. And we can also measure other thermodynamic variables for this, such as the pressure, temperature, entropy. I'll try to list them all here. Entropy, S, and we'll even put chemical potential on the list. So that one's too long to write, so I'll just put chem pot, lowercase mu. So we could measure each one of these quantities for our sample. But what we want to consider in the difference between intensive and extensive is how each of these quantities is going to change, is going to get scaled if we make our sample a little bit bigger. So let's consider another sample, which I will call, let's do this in a different color. Let's say in green. We've got this sample here in the green outline. And that one is V prime. Okay, so it's a little bit larger sample. It encloses the volume V inside of itself plus some additional amount. So V prime is larger than V. And one way to represent this increased volume of the sample is to write V prime as some multiple of V. So lambda is a multiplier here, and it's, with the box being bigger, it's greater than 1. So if we make our box bigger, let's ask ourselves how each of these quantities would change. Remember, we're inside of some much larger thermodynamic object here. So clearly, the V prime for the volume is going to be larger because that's what we chose. What about the number of molecules? Well, we're just including a larger region of space. We're going to have more matter in there, right? So the number of molecules is going to go up as well. So n prime will be scaled up by the same factor. So will moles. That's not really different than number of molecules. And the internal energy will also be scaled up, right? If we include more matter, then we have all that new matter is also moving and interacting, so it just has more energy altogether. But what about the pressure of the matter contained within V prime? Well, just because I've drawn a larger box doesn't mean that that matter can exert a larger force, right, per area. We just kind of drawn this imaginary line around it. So if this thing is in equilibrium, it has the same pressure everywhere throughout itself. So drawing a box around it doesn't change the value of the pressure. So when we scale up the size of our sample, the pressure here is the same. What about the temperature? If it was in equilibrium, the temperature is constant everywhere already, so changing the size of the box doesn't change the temperature. See if you can guess what happens to the entropy. It might be hard because entropy is a little bit different concept, but let's see if we can do a little bit of a proof here. Remember a while ago we had a proof that if we combined two systems that were independent, that the multiplicity of the overall system would be the product of the multiplicity of each part. All right? And then we also had a proof that if we combined n systems together, that the multiplicity of the total would be the multiplicity of each one raised to the nth power. Okay? So it makes sense then that the multiplicity scales multiplicatively when we increase the size of the system. So in our case here, if we have the multiplicity at volume V prime versus the multiplicity at volume V, we would expect that to be raised to the power lambda. So if lambda was 1, they would be the same. If lambda was 2, there would be twice the volume, and the multiplicity would be the product, right, squared. And if lambda was 3, there would be 3 times the volume, and the multiplicity would be the cube of the original, right? So that's logically how the multiplicity scales, just because it's a counting of number of unique states. Now remember that entropy is the logarithm of the multiplicity. Times some constant, right? Whatever. So if we take the logarithm of the multiplicity for the increased size, then this power will come down to the front. That's one of the rules of logs. So entropy also scales up. It grows just like energy and number of particles. The last one on the list, chemical potential, not so familiar to us, but again, it's a quantity that's constant throughout the whole region. It's it's something that determines whether there's going to be a favorable chemical reaction or something. The system's in equilibrium, so there's no gradients in chemical potential either. So this also, in the increased system, just stays the same. So let's look at our list of scaled numbers. Here we see that all of our thermodynamic measurements, really, there's only 2 different ways they behave when we scale up the system. Either they stay the same, like pressure, temperature, chemical potential, or they get scaled up by the same proportion, volume, number, energy, entropy. The ones that are scaled up by a proportion are called extensive. An extensive quantity is one that scales in proportion to the size of the system. So these ones here are all extensive. Entropy is extensive. Quantities like pressure and temperature and chemical potential, these do not change when we scale the size of the system. They are called intensive variables. So that's the difference between intensive and extensive. It's whether it scales when we look at a larger region of space for the sample or not. Now, every thermodynamic variable can be classified as either intensive or extensive. So let's go back to some of our old equations and see if things make sense. Here's an old equation, ideal gas law. Okay, so what's going on with the scaling of the ideal gas law? If we apply the ideal gas law to our original sample, then it's PV equals nRT, no primes. If we apply the ideal gas law to our enlarged sample, we'll just throw a prime on all the quantities. And let's see if, if this still makes sense. So P prime, pressure in the new one, is the same as P. The volume gets scaled up. V prime is lambda times V. The number of moles gets scaled up, lambda times N. The ideal gas constant stays constant, and the temperature stays the same. So what happens here is the lambdas cancel off of each side, and we just retrieve the original ideal gas equation. It would be a pretty bad day if just looking at a larger window of the matter broke the ideal gas law, right? We wouldn't want that to happen. So we're very fortunate, it appears, that the number of lambdas that appeared in the equation, there and there, was the same power on both sides. So this gives us actually a general principle for any equation in thermodynamics that we claim to be true. It must have, any equation, let's write this out, any equation must have the same power of the scaling factor on both sides. So any proposed equation must have the same number of extensive quantities on each side. The intensive ones we don't really care about because they don't change when they're scaled at all. But the number of extensive quantities has to be the same on each side. So you go back and look at the ideal gas law, you'll see, well, where are the extensive quantities? It's volume and moles. So there's one of those on each side. So this equation is consistent under scaling. Let's go back to a more complicated equation. Here's one of our favorites from back in the day. The good old Sackur-Tetrode equation. Probably one of the longer equations that you're actually expected to use to get a number in physics. Well, let's look at the scaling. Where do the extensive quantities show up? Let's underline them in green. So entropy on the left, one extensive power. Moles on the right, one extensive power. R is a constant. So apart from the stuff in square brackets, we look like we're okay. We have one extensive quantity on each side. Inside of the square brackets, we've got to make sure that stays consistent as well. 5/2 is a constant. There's no problem from that. What about the argument of the logarithm? Well, here we've got volume, which is extensive, divided by number of particles. If we take the ratio between two extensive quantities under the scaling, that scaling factor cancels out and we get the same ratio. So if we have things like densities or quantities per mole, molar volume, molar internal energy, those will also be intensive because they don't scale. They have the same value before and after the scaling. Right? This lambda cancels out. So inside of our logarithm, back to here, we got the v and the n. The ratio of v to n is an intensive quantity, so that doesn't change. Where else do we have intensive or extensive quantities? Pi, m, h bar, those are all constants. Only u and n could change with scaling, but again, we find them in the ratio of u divided by n. This is an energy per particle, which makes it an intensive ratio. So inside of our logarithm, we have all intensive quantities. And that is another general principle of consistency with these equations, is that any value that gets input to a special function, exponential, logarithm, tangent or something, any value that goes into one of those must be unitless, and also it must be intensive. We can't have our equation break just because we considered a larger region of space. So let's write that out too. Inputs to special functions must be intensive. Okay. Now let's look at some equations that we haven't seen before. In fact, I don't expect anyone to have seen these before, and I don't really expect anyone to see them ever again because I'm going to make them up on the spot. Let's say we wanted to modify the ideal gas law. And we thought maybe instead of just multiplying by the volume, we should somehow improve our ideal gas law by multiplying pressure times volume plus a constant times volume squared. All right. Now that seems entirely possible. We can just happily plug in 5 liters here and 5 liters squared there, and the constant can be in units of inverse liters, and unit wise it's all great. The numbers seem fine. But if we consider the scaling of this equation with larger and smaller systems, it becomes obvious that this equation is an impossible modification, could never represent any true physical process. Here's the reason. Let's look at the scaling. Let's say that we just increased the size of our system a little bit to V prime. Well, the pressure stays the same. The volume gets scaled up. Constant A doesn't change. The volume prime here is scaled up before it gets squared. So we've got a lambda squared there, and that's going to be a problem. But let's finish. Over on the right side, have lambda times n, the scaled up value, times r. Oh, sorry, this was t prime up there, which scales to t anyway, so I can be forgiven. But when we look at the scaling of this equation, we can cancel the lambda partially, right? There's one here, at least one here, and one here. So we can cancel some of the lambdas, but not all of them. A scaling factor remains on this term. And so what that means is that we could maybe get some numbers out of this equation for a particular volume, but if we just tried to apply it to the same matter with twice the volume, we would get a totally different answer for the pressure, temperature. It wouldn't make any sense at all, right? So this equation cannot be true as a modification to the ideal gas law. It actually gives us quite a powerful way to think about what equations are possible and what equations are impossible. So what can we do? Maybe we really wanted to add this term. We think it makes a good sense to put this there for some reason. What can we do to make it work? Well, we have to make sure that everything on the left side has exactly one intensive variable when it's all multiplied out. So pressure times volume is one intensive variable. Pressure times A times volume squared is 2 intensive variables. So if we were to divide that term by some other intensive variable, then it would work out. So what if we took pressure times the quantity, volume plus a constant, times volume squared over moles? How would that fare when we did the scaling? Well, let's plug it in, all right? Pressure prime would be the same as pressure. The volume would get scaled up. Here we'd have lambda squared v squared. And in the denominator, we would have lambda n. Over here we get lambda n times r times t. So now in the scaling, this n in the denominator gave us an extra scaling factor, which can cancel there, leaving every term with a single power of lambda, which can be canceled, and the equation stays true. So this is a plausible modification to the ideal gas law. At least it's consistent with scaling. It might be totally bogus in terms of getting any good predictions, but at least it doesn't break if we just make the system bigger or smaller. All right, so this is the general principle for checking any equation to see if it scales correctly. Replace all extensive variables with lambda. So let's see. Replace all extensive variables a with lambda times a. We can then say that's step one of the check. Step two is to leave intensive variables alone. So temperature, pressure, chemical potential, density, we can just leave those the way they were. All right, and then after we do these replacements, the simplified equation must be independent of lambda. Okay, if it's independent of lambda, then it could be a correct equation. It agrees with the scaling behavior of nature. If it depends on lambda, then it must be rejected. It couldn't be a possible equation even if it looks kind of okay.